Good morning. I'm Kefei from Tsinghua University. Thank you for inviting me for this Rilem anniversary keynote presentation. I would like to take this opportunity to give my best wishes for Rilem to keep its young dynamism and innovation in the future as in the past. My topic is on durability design and planning for concrete structures in Hong Kong-Zhuhai-Macau bridge. And first, I will introduce this project to you, and then I will successively talk about the durability design, quality control, and the durability assessment and maintenance planning. In the end, I will summarize my talk. First, let's look at this project. The Hong Kong-Zhuhai-Macau Sea Link Bridge link Hong Kong to China mainland here to Macau and Zhuhai. It consists of a sea bridge of 28 kilometers, two artificial islands, and a segment of immersed tube tunnel of 6.8 kilometers. The design working life of this concrete works is 120 years, and it's a challenge for concrete structures in marine environment, aggressive marine environment. And the design work started in 2010, and it has been open to traffic in 2018. And reinforced concrete is used extensively in this project. You can see that reinforced concrete is used in integral pylon, pier, bearing platform, in the span of bridges, and also the tube segment in the immersed tube tunnel. Here are some images during the construction for bridge for the tube segment and the artificial islands. Here is the view of the finished works. Then we look at the durability design of these concrete structures. The situation is that we are facing multiple durability process. So the first task is to classify this process into different risk levels. Here you can see that after comprehensive analysis, we attribute low risk level to salt attack, alkali aggregated reaction, delayed intragat formation, and a higher risk to the chloride induced or carbonation induced corrosion. For these two groups, we adopt different strategies. That means for the lowest group, we accomplish the durability design through the control of the raw materials. But for the higher risk, we need model-based method to really make the design. And for the design parameter, we consider both the parameter at material level and the structure level. For example, for the chloride-induced corrosion at the material level, we will consider WB ratio, bonder type, bonder content, and the initial chloride content. At structural level, we will consider the cover thickness, the cover quality, and the quality control, the crack control. So we will use model-based approach to solve the durability design for these two corrosion-related processes. When we talk about model-based approach, the fundamental concept is that we should have a model, a durability model, to be capable to describe the deterioration law of the performance with respect to very clear durability limit states and service life. So in the design procedure, we begin with the specification or quantification of the environmental actions and the design service life. And then we input this data, this information into the model. So with, of course, specified the durability limit states, the model can give us quantified results. From interpreting these results, we will formulate the requirements for durability for the material quality, protection measures, and the element details as well. Okay. So here I will show you the DLS and the service life attribute to the principal elements. You can see that for the principal reinforced concrete elements, they all have the same design working life as the whole project, and the durability limit states is specified as the corrosion initiation. Okay. Then the durability model. The model we used is very similar to the model from Duracrete or FIB model code, except that the statistical property of the variables like the initial chloride, the surface chloride, or chloride diffusivity here should be calibrated to the exposure conditions in the project site. That's the problem. First, let's look at how to handle the statistical variables in the durability design. Here, I introduce briefly how reliability theory tells us to do. If you have a design equation here with statistical variables, you can use full probability approach to calculate directed failure probability of your design equations. And then the reliability theory can help us to calibrate a more engineering format of this solution. That is a set of characteristic value and a set of the partial factors associated with that. That is what we have done to handle the statistical variables. The second problem is the statistical property of these parameters. We are very lucky in this case to have long-term exposure data of 30 years, nearly 30 years in a very similar marine site, not very far from the project site. So using this exposure data, we were able to calibrate the statistical properties for cover thickness, for the surface chloride concentration, and the critical chloride content, etc. So by all this data and the regressed statistical properties, we finally calibrate the partial factors for this main parameters all together with their characteristic values. Here are the result. So by this equation, engineers can calculate easily the quantified requirements for durability. Here I show you one of the main results here. For example, we prescribed the durability requirement for different elements here in terms of the cover thickness and the design value for the chloride diffusivity. Then during the construction, we should assure the designed durability performance to be realized through the construction procedure. For this purpose, we install a global scheme for quality control, including the control of compressive strength, chloride diffusivity, cover thickness, and also the surface properties like air permeability and electrical resistivity. Here, I show you how we cope with the chloride diffusivity here. The first task is to convert the design value of chloride diffusivity to the measured value or measured value in laboratory. The difference is that the design value is a diffusion, is a no steady state diffusion value, but the laboratory measured value is the migration value. So we establish the correlationship between the two values and convert the design value to quality control value. And then we establish the compliance criterion for this chloride diffusivity. And then with the collected data, we can also perform the first durability assessment for the achieved durability of performance during the construction. The model is very similar to the design model, except that we convert the migration value measured in laboratory to design value by this correlationship coefficient, and consider the protection measures such as the stainless bars, epoxy coating, impregnation, and cathodic protection, etc. Here you can refer to this reference to see the statistical property updating for cover thickness, for the surface chloride content, and other parameters. Here are the durability assessment results. From the result, you can see that all the durability performance from the assessment is always better than the performance level expected in design phase, in the design. So on the basis of this assessment result, we can already make the first maintenance planning here. For example, for the element without stainless bar, here we proposed a surface maintenance period of 20 years. And what really can make successful maintenance planning is we should activate the inspection and monitoring and durability assessment and the maintenance actions. It works like this. We collect the data from inspection and monitoring, and we feed into the durability assessment to see if the result is satisfied or not. If not, we will activate the maintenance actions. Here is something we are doing now. We are establishing the durability database, including the surface condition, the long-term monitoring and inspection, and also the long-term exposure data. And we are also establishing a model library for durability. That means in addition to the basic durability model for chloride ingress and carbonation, we will consider also the corrosion development, cracks, surface leaching, carbonation, true surface action, and protection effects, etc. So here I just show you some most recent results. From the exposure data, we get the exposure data of 3 years. We use this data to update the chloride content of surface and apparent diffusivity. And then we update the failure probability. And with this result, we can update the period of maintenance for the sealant impregnation from 20 years to 40 years, for example. So I summarize my lecture here. The first point, I think, is durability of concrete structures should consider the statistical property of the main parameters, and these parameters should come from the long-term exposure data. And then the construction, the data we collect in construction phases can help us to make the quality control and durability assessment. And then during the surface phase, the really successful maintenance planning should activate the data inspection, durability assessment, and durability maintenance. And in the end, in the future, I think the durability planning should of large-scale concrete works should incorporate more deepened durability models, more method of quality control in construction, and more inspection and monitoring for maintenance planning in service life. Thank you for listening.